Hi guys, today we are going to talk about shortest path algorithm. First of all, definition. A shortest path from vertex S to vertex T is a directed path from S to T with a priority that no other such path has a lower weight. Now, to compute the shortest path, we use the edge-weighted digraphs. So now the edges are directed, but they are weighted. And the problem that we are going to be looking at is to find the shortest path from one vertex to another. So in this example, we've got a edges, directed graph with a variety of the directed edges. And our goal is to find, given two vertices, let's say 0 to 6, find what is the shortest path that takes us from 0 to 6, where the length of path is the sum of its weights. In this case, the shortest distance is from 0 to 2, 2 to 7, 7 to 3, and 3 to 6. Now the algorithms that we're going to look at for this are classic algorithms. When you have a map and you want to get one place to another, get from one place to another, or you have a device in your car that gives you directions to get from one place to another. These devices are implementing the classic algorithms that we are going to talk about today. Shortest path is a really interesting and important problem-solving model. So, one thing is, what vertices are we talking about? So, of course, the most familiar is so-called source link. What's the shortest path from one vertex to another? But actually, more useful often is so-called single source shortest path, which is all the paths from one vertex to every other. And this is the one example that the navigation system in your car might use. The source is where you are, and it will compute the shortest path to every place else, and then when you ask for some place, it will just pick one that you want in a manner very similar to the API that we are going to talk about. Another thing that you might do if you didn't have many vertices is compute all pairs of shortest paths, so pre-compute the path between all pair of vertices, and then immediately be able to direct answer a client query. Usually we think of it in terms of positive edge weights because the maps are geometric, and so the length of an edge is proportional its distance in the plane. But actually, for many problems, they may be much more arbitrary, and actually, one of the big issues that we'll see is whether the edge weights are positive or negative, and does the graph has directive cycles. In particular, whether the total length of a cycle is negative or not, we'll get to that at the end. So that's the introduction to our shortest path. In the next what about we'll talk is the algorithms that we use for computing and defining of shortest path. Now we'll look for a Dijkstra's algorithm for finding shortest paths in graphs with non-negative edge weights. So let's take a look at how that algorithm works. It's a very simple algorithm. What we're going to do is to consider the vertices in increasing order of distance from source. So, and the way we're going to do that is take the next vertex, add it to the tree, and relax all the edges that point from the vertex. So let's talk about in terms of a demo. So our source is 0 in this case. So what vertices are closest to the source? Well, we can look at the edges that point from the vertex. Start out with vertex 0. Then we add that vertex to the shortest path tree and relax all its edges. Okay, relax. By the way, what does relaxation do? Relaxation ensures that after the relaxation, either way there was before, Afterwards, you have the distance to W is less than or equal the distance to V plus E to the E plus the way to the edge. And relaxing all the edges pointing from 0, in this case it's just going to update these 2 and edge 2 entries for 5, 8 and 9. So in this case it says that the shortest path from 0 to 1 is to go along 0, 1, and that's distance 5, and from 0 to 4 it's to go along 0, 4, and that's distance 9, and so on. And the edge weights are positive, we are not going to find the shorter path to anyone. The edge weights are positive, and those are the shortest paths that we know so far to the vertices. Now the first key point of the algorithm is take the closest one. If you take the closest one, in this case it's 1, then we know we are not going to find a shorter path to 1. Okay, we pick 1. Then we know the only other way to go out of 0 is to take one of these other edges and they are longer. So we are not going to find a shorter way from 0 to 1 than to take the edge 0, 1. So that means that the edge 0, 1 is the shortest path 3. That's what the algorithm says. Take the next closest vertex to the source. In this case, it's 1. And then we are going to add the edge that vertex to the tree and relax all the edges that point from that. Now, both 0 and 1 are on the tree. So now let's look at the edges pointing to that, and we have to relax each one of those. So in this case, if you go from 1 to 4, then we look at 4. We know a path of length 9. And 1 to 4 doesn't give us a shorter path, so we leave that edge alone. 1 to 3 gives us a shorter path to 3, which is going to be 20, because you went from 0 to 1, and then 1 to 3 is length 20, and 1 to 2 is also, we didn't know, now a way to 2, but we know now 1, or better, 1 is 17. So that completes the relaxation of all the edges pointing from 1. So now we have a 0 and 1 on the tree, and we would consider the next closest vertex to the source. So what we have in this 2 is the shortest path to all the vertices that we have seen so far. In this one says that we have been to the 0 and 1, so the next closest is 7, which is distance 8. So we are going to choose vertex 7, and again that's the shortest path we have seen so far. We are not going to find the shorter one because to get every other vertex is longer, and so we know that it's on the shortest path tree, and we are going to relax all the edges pointing from 7. In this case, both of them, the one from 7 to 2 gives us a shorter way to 2 than what we knew before, and the one from 7 to give us a shorter way to 5 than we knew before. Well, we hadn't been to 5 before, so that relaxes 7, and now 7 is on the shortest path tree. So now force the next closest path vertex to the source. From the edge 0, 4 which is of length 9, so that the one that we are going to pick the next for the tree. We are not going to find a shorter path there. And we relax along all its edges. In this case, we find a shorter path to 5 and than we knew before here, and a shorter path to 6. Well, we visit 6 for the first time. Okay, that's 4. So now we just have to worry about 2, 3, 5, 2, 3, 5, and 6. And so we select vertex 5. Relax along these edges. In this case, those edges both give us better paths than we knew before. So now we're left with 3 vertices, and now we're left with vertices, and 2 is a winner. This is a 2 from the source 14. So 3, it's 20, and to 6, it's 26. Relax its edges. And it gives us again new shorter paths both to 3 and 6. And then this next to last step is to pick 3. And that doesn't give us a new way to 6, and then finally we pick 6. And then we know now the shortest path to all the vertices from vertex 0. If we just take the edge to edges, just that's to 1 you take 0, to 5 you take 2, and so forth you get the shortest path tree, and that gives the shortest way to get from the source to every vertex. That's a simulation of Dijkstra's algorithm. It gets the running time down to e plus v log v. Of course, in your graph is dense, and again, the example I used they are not. The array implementation is optimal. We can't do any better. We have to go through all the edges and might as well find the minimum at the same time. Now we are going to look at the shortest path and edge-weighted tags. This is a very common situation. Suppose that you got an edge-weighted tag graph. That's our input in shortest path. But you know that there is no directed cycles, and actually that's true, and in many applications we see some. The question is this: fact that has no directed cycles make it easier to find the shortest path than in a general digraph. And the answer is yes, it certainly does. And the algorithm is very simple. What we're going to do is just consider the vertices in topological order. Since there is no cycles, we know there is a topological ordering where we can lay out the graph and all the edges point to vertices that we haven't seen yet. And so we just relaxed all edges pointing from each vertex, taking them in topological order. So here's the edge-weighted tag. And the first thing that we do is sort the vertices in topological order. And then do the same job as in previous example about Dijkstra's algorithm. Starting from vertex 0, relax it, and then take the next vertex. We'll look for a Bellman-Ford algorithm for finding the shortest path. So let's look at the method of working. What we are going to do is pick the vertices and relax all the edges in adjacent list of this vertex and repeat v times. So we start from vertex 0, then relax all edges, which is starting from 0. And we have finished first pass, and we start next pass again. And then finally we finished with passes. First pass, and then nothing changed in second, third, fourth, fifth, and seventh passes. It means that we already have this table. This is all about Bellman-Ford. One of the main applications of shortest path is seam carving. It's about resizing an image without distortion for display on cell phones and web browsers. Seams can be either vertical or horizontal. A vertical seam is a path of pixels connected from top to bottom in an image with one pixel in each row. The energy function values a pixel by measuring its contrast with its neighbor pixels. After computing the seam, we have to delete the seam and repeat till the size of screen. Computing the seam consists of finding the path of minimum energy cost from one end of the image to another. There you can see the result of this algorithm application. Thank you for watching. Like this video, subscribe, and that's all.